Hello everyone. As promised, here is a video on antenna matching, the way I do it anyway. Other people have different methods, different ideas, different techniques. This is the way I do it on my designs, and I'm sharing this with you. I'm going to start out with a simple 433 megahertz design using a pretty common device called the CC1101. This design has already been established. I've used it for a few years, and I'm actually just deconstructing it now for the purposes of this video and how I did the match and set the VNA up. We're going to start this video out with the design process, where to add the matching elements and on the PCB, and then we'll move over to the VNA. That'll be a separate portion of the video. So let's get started. I'm going to zoom in here and show you what I'm doing here. I'm going to turn this off because you don't really need to see my mug through the whole thing. So let's get going. Okay, so on the screen is let's see here. I can do this here. This is a board I designed about 2 years ago. And let's see, I got to turn off my mountings, turn off these other parts that don't need to be there. Let's see here, and there's J1, J2, J3. This is a board I designed for a customer. It's a key fob. He had already purchased 10,000 or so plastic key fob cases, and I had to design this thing around a previous transmitter that he could no longer get from overseas. So that's why these push button switches are the way they are. This was the best step file I could find for these. The actual switches, the leads bend underneath. I guess I could go into SolidWorks and edit those at some point in the future, but I'm not that concerned about it. So anyway, I had started this design out with a chip antenna that I had placed below D1, and I'll get to D1 here in a second. I didn't like the performance of it. I matched it. I just didn't like the performance of it. I tried a couple of different techniques, and finally I decided to just draw this squiggly line monopole thing in here. Just play just as a let's see how this thing works. Lo and behold, it outperformed 2 to 1. The range is fantastic once it's matched properly, which is a little bit of a pain, but once I got it properly matched, this thing really performed well. I know somebody's going to talk about the LEDs, so I'll bring that up. Again, the customer had already purchased these plastic key fob enclosures, and they came with a little LED in the middle there, and he insisted on I keep that, so I had to put this little red blinking LED there in the middle of my antenna. All right, so we'll go over here. I guess I should bring up my schematic. I forgot to bring that up too. Allegro X. They're just changing my name on me here. Here we go. Oh, while that's opening here, I'll go back to this is the 1101. This is the circuitry. Let me highlight some things here. This area of the circuitry comes from the manufacturer, and if you scroll down through the data sheet, you'll find predetermined values for these components based on your frequency range. The 387 to 464 frequency range has a set of values called out in the data sheet, which is what I used in my schematic. And we'll open that up. And we're going to open. Come on. Could be a little faster. Let's delete this. And my matching element, what we're going to focus on is right there. We're going to add the matching element there. Okay, so here is the 1101's predetermined circuitry. It ends at C1 right there. And here is where I add a pi filter. It's a generic pi filter. This is an already established design, so these values have already been determined through tedious amounts of testing. But you just add placeholders for Z1, Z2, Z3. Just dummy placeholders, because they can be anything. They can be two capacitors, two inductors. It can be high pass filter, low pass filter. It all depends on where your antenna during the testing phase, where its complex value falls on the VNA Smith chart. And this happened to be this low pass circuitry. So I always add this note here because data sheets like to call out values. For example, you'll buy an antenna and it'll have some predetermined values for the match. Well, those usually will get you close. Sometimes they'll work perfectly. Sometimes they'll be a little bit off because it depends on the design itself. If the demo board was an 062 board and you're using an 031 of some different material, the matching could be a little different. You know, the parasitic inductance, capacitance, and whatnot is going to be a little different. So you might have to tweak those values. So I always make sure that everyone knows that even if the customer gives me an antenna and says use this one and here's the matching, you've got to test it first before you sign off on production. So this is it, and let's see, we'll go over to the board now and we'll see here, we'll zoom in, and this is my Z1, Z2, Z3. They're actually not all populated, so this is actually what it looks like there. Z1, Z3 is not populated, but Z1, Z2, and Z3. Once we get over to the board, I'll show you, I'm going to take zoom in pictures of the board itself. I like to connectorize, if that's a real word, I like to connectorize as much as I can. So let me turn off Z. So right at this point right there, I have an SMA. I have an SMA connector, if you can see the little box I'm drawing there. Maybe I'll take a screenshot and I'll show you. You'll see this an actual snap of the board itself. So there's an SMA that I've clipped, an end launch SMA where I've clipped some of the leads off, I've trimmed the center pin down, and I solder it right to there without none of these components are installed on the bare board. Keep in mind, we're testing a bare board. We're not testing the circuit functionality, we're testing the antenna. So I test it here. I solder it to there. So you've got this little area there that it's connected to, and leave Z2 open because we're just connecting it up right now, and we'll get over to the how to set the VNA up here shortly. So I believe, let's see, what else do I need to cover before we go over to that? I think that's about it. I'm sure I'm forgetting something, but I just needed to point out that keep in mind, pay attention to Z1, Z2, and Z3, especially Z1 and Z2. Because so what we're going to do is once we set up our VNA and once we've got the SMA connector soldered to the board, we're going to leave Z2 open. We're going to calibrate the VNA. Then we're going to connect the board, and then what you have to do is you have to enable port extensions, and then you have to add this length here you have to add this length here to your port extension. I can multi-select there. So this whole length gets added to the port extension. You have to do that or you're not going to get the right values in the Smith chart. And we're going to leave Z2 open because we don't want to connect the antenna. Once we have the port extensions done and everything's dialed in, then what we're going to do is solder short. You can use a 0 ohm jumper if you want. These are 0402 components, so I just use a little solder short. So once we have the VNA set up, we're going to solder short this Z2, and that's going to add the entire antenna. The entire antenna's electrical length to the testing. and that's going to give us, the VNA is going to then show us a complex value of what the entire length of this antenna looks like. And those numbers, that's going to give us a number. It's going to give us a complex number if you're familiar with the complex number system. And we're going to take that and we're going to put it into a calculator. There's a lot of calculators out there. There's one from Analog Devices that I use where you enter in your frequency and those complex values and the target impedance, and it'll spit you out the resultant number that you need to add. It actually gives you a circuit too, high pass, low pass, you know, the inductors, capacitors. Actually, I can go over to that. I'll go over that in a minute. Okay, we're over at the VNA now, and we have to calibrate it. This is a 433 megahertz antenna, so we're going to say center, 433 megahertz. Span, I can use a 50 megahertz span on this one. These are pretty narrowband antennas. I'm going to add a marker at 433 megahertz. And we're going to go to Cal. I'm going to select my Cal kit here. This is a custom Cal kit that I had to enter the parameters of manually and save it as a kit. I call it good because it's good. I know it's good. So we're going to go to calibrate. One port cal. We're only looking at S11 on this. So we're going to add our open standard. Open. Short. And load. Done. Return. Go to format, Smith chart. There we go. Now we've only got the cable. This is an SMA cable. I've got some ferrite beads on it to quell the surface currents. It's a semi-rigid cable. Those are pretty good quality. We do not have the board connected yet. Now this is the important part. Now we're going to connect our board. And remember, we have the SMA attached to the board just to the left of Z1. We have Z2 open, so we're not measuring antenna. What we're going to do here is we have to add port extension to add the electrical length of that SMA and that small amount of PCB material. If you don't do this, you're not going to get the right results. You'll notice now that the board is connected, our open is down there. So what we need to do, we go to Cal, go to port extensions. We're going to turn the port extension on. This particular VNA has a way to auto calibrate this. If your VNA doesn't have that, we'll go to, I'll show you this, we go to port extension and you just spin this dial until you get to that open point there, right about there. I'll show you this as well. Auto port extension, measure open, one port there. So some people like to look at the phase. You can look at the phase as well to make sure this is perfectly flat. So we know we're good now. So format, Smith chart. So that is the important part. If you don't do your port extensions, you're not going to get the right results. So now what we're going to do is we're going to disconnect the board. I'm going to solder short Z2 and we're going to measure the antenna. Okay, so we have Z2 shorted now, and now we are measuring the entire antenna, the electrical length of the antenna. We're getting the complex number of the antenna. This is the number that we're going to put into our calculator to tell us what kind of match we need. And you can see it's bouncing around a little bit. It's going to do that. Roughly 8.1 minus 165. That's what we're going to put into our calculator, again, to show us what kind of match we need. Okay, now that we have our complex value from the VNA, the antenna measurement anyway, at 8 and minus 165, we're going to go over to an online calculator. One that I like to use is from analog.com, and we're going to enter that information in here. Let's go back to the default values. So you want to enter your frequency. You can leave this at single-ended series complex load 8 minus 165, and it's going to spit out some configurations here. If you're not familiar with Smith charts, there's what's called the forbidden zone. You can Google search that and it'll give you some images of where the forbidden zones are. Smith charts are a funny thing. You can't go in every single direction from every single point on the Smith chart. You have to follow these lines, these contour lines, and you have to use the appropriate method to get there. I can show you this if we change this to like a 90 or something. You can see that the configuration changes. Let's see here, I'll go back to my 8, and this gives me a low-pass inductor capacitor and another inductor configuration. I prefer using the inductor capacitor configuration. Obviously 67.386 is pretty close to 68 nanohenry, which is a standard inductor value. And capacitors I just find easier to work with. They come in much smaller increments. I actually have a 0.1 picofarad capacitor that I can add in parallel when I need to tweak by very small amounts. So this is what I like to use. You can also use a Smith chart tool. There's one from Fritz Delsberger. If I'm pronouncing your name incorrectly, sir, I apologize. You can download his Smith chart tool. I believe he accepts money for the full version, if he is still accepting money, that is. It's been a while since I've downloaded the tool. So anyway, here's the matching network that we're going to use, this 67 or 68 nanohenry and 16.8. We're going to see just how close that comes. Okay, so here's the final product. I have a 68 nanohenry inductor installed, and I believe a 13 picofarad capacitor on this board. The schematic says 12 picofarad. I can update the schematic, or I can either the 12 or 13 worked fine. This is a cheap FR4 board. There are differences between. I've matched probably 24 of these exact boards, and I get a little bit of differences because, again, it's cheap FR4. This is not a Rogers material. There are differences. There are part value differences. So the tough part of this project is you're going to put your complex number into the calculator, and it's going to give you some values, and you're going to put those values, or as close as you can get to those values, into your board, and you're going to say, Ken, what's going on here? The thing's not, thing doesn't look right. It's not matched. Well, there are tolerances. You know, again, the calculator wanted to use a 67 nanohenry. There is none. I had to use a 68. Said something like a 16.8 picofarad. I ended up using 13 picofarad. So there's a little differences, part tolerances, parasitics on the board. There's also is the inductor actually 68 nanohenries at 433 megahertz? Probably not. The capacitor might be a little bit different at 433. You can use your VNA to test that if you didn't know. The VNAs actually work as an LCR meter. So you can test individual components. But this works out pretty well. 68 nanohenry inductor, 13 picofarad capacitor on this board. Previous boards I've used a 12 picofarad. Either one works. This is pretty close. 433.25. You're not going to get any closer than that on just a monopole N10 on a cheap FR4 board. Let's see, we'll go to Smith chart here. 49.6 ohms. You're not going to get any better. This is done. Now, people are going to comment, well, this thing goes into an enclosure. What do you do about that? Of course, if I had access to the enclosure, which I don't on this particular design, I would put it in the enclosure and measure and make my match according to that. In previous designs, I've had the enclosure. I worked on a 915 megahertz transmitter, very similar design, just higher frequency, where it sat inside a watch type case that the patient wore on their wrist, and that one I actually soldered some wires to it and had them hanging out of the enclosure, and was able to do the matching inside the enclosure and sitting on my arm, which was challenging to say the least. But I was able to do it. So if you have access to the enclosure, by all means, go ahead and do that. If you don't have access to the enclosure, this is the best you're going to be able to do. You have to tell your customer, hey, this thing's matched at the frequency you wanted to run at. Here it is, here's my plots. So I'm sure I'm missing something, I'm sure I'm forgetting something. Please add what you want into the comments section, ask some questions. I'll try to answer as many as I can. But I hope this helped. Thank you.